Imagine a house that survives a Category 5 hurricane, that a tornado tears through and walks away from, that you could literally light on fire and it wouldn't burn. Now imagine, almost nobody's building it. Not because it's too expensive, not because the technology doesn't exist, but because of something far stranger than that. This is the story of the most resilient structure humanity has ever designed for everyday living. And the deeply uncomfortable reason it almost completely disappeared. Look at that. Doesn't it look like it landed? Like something from another century or another planet entirely. This is a monolithic dome home. And the first time most people see one, they feel two things at once: fascination and a quiet, nagging sense that they've been lied to. Because here's the thing. This technology, this idea, is not new. It's not experimental. It's not theoretical. It has been tested in the most brutal real-world conditions imaginable, over and over again. And it passed. Every single time. So why, when you drive through any city, any suburb, any neighborhood in America, do you almost never see one? Why are the streets lined with wooden boxes covered in drywall? Structures that crack, flood, burn, and collapse when this exists? That's the question that's going to haunt this entire video. And here's the first hint I'll give you. This isn't a technology problem. It never was. Go back 15,000 years. You're standing on the Mammoth Steppe, modern-day Ukraine. There are no trees, no lumber, no flat walls anywhere in sight. But there are people, and they need shelter. And what do they build? They take the curved bones of woolly mammoths, massive arching ribs, and they stack them, lash them together, cover them with hide. A dome. Not because someone told them to, not because they had engineering degrees, but because nature showed them. Because the arch, the curve, is how the natural world holds weight. It's the shape of skulls, of eggshells, of caves, of the sky itself. They didn't have equations, but they understood something we forgot. Fast forward a few thousand years. 118 AD, the Roman Empire is at its peak. And they're about to build something so structurally perfect that it will stand completely intact for nearly 2,000 years. The Pantheon. A dome with a hole in the top. No steel, no modern concrete. Just Roman ingenuity and a deep understanding of how curved geometry distributes force. Here's the wild part. The Pantheon's dome is still the world's largest unreinforced concrete dome, built before electricity, before power tools, before anything we'd recognize as modern engineering. And it's still standing. Now jump to the Middle East, to the Persian Empire, to the Byzantine world. Dome after dome after dome. Mosques, cathedrals, markets, tombs. The greatest buildings of every great civilization converge on the same conclusion. The dome works. So why in the modern era did we abandon it? Why did we choose the box? Simple. Industrialization. When the 20th century arrived, it brought with it assembly lines, mass-produced lumber, standardized windows, cookie-cutter floor plans. Building a box was fast. It was cheap. It was repeatable. And so we forgot the dome. We filed it away as something ancient, decorative, impractical. And that forgetting? It has cost us in energy, in disaster, in money enormously. Here's the secret nobody explains in school. Flat is weak. Not because it looks weak, not because it feels weak, but because of physics. When force, gravity, wind pressure, impact hits a flat surface, that force has nowhere to go. It concentrates, it builds, it finds the weakest point, and it breaks through. That's why flat roofs cave under snow, why box homes shatter in tornadoes, why a rectangular wall, when hit from the side, has almost no resistance. Now look at a dome. When force hits a curve, something extraordinary happens. The load doesn't concentrate, it travels. It follows the arc of the structure, moving along the surface, distributing across every square inch, and finally driving down into the ground. The dome doesn't fight the force, it redirects it. Engineers call this compression-only structure. The entire shell is always in compression, meaning every single point is pushing inward, bracing against itself. It's like an arch you can live inside. Here's an analogy that might actually break your brain. Take an egg, a chicken egg. Now try to crush it, not by cracking the shell, but by squeezing it evenly between your palms. You can't. That thin, fragile shell, thinner than a piece of paper relative to its size, is almost impossible to crush with uniform pressure, because the curve distributes the force so perfectly that no single point gives way. A monolithic dome home is, essentially, a giant concrete egg. And the numbers back this up. The shell of a properly built monolithic dome can withstand winds in excess of 300 miles per hour. 300 miles per hour. For reference, the strongest recorded tornado wind speed ever measured was 301 miles per hour. The secret isn't strength, it's shape. Here's where the story takes a turn. Because knowing the dome works and actually building one as a house are two completely different problems. For centuries, domes required massive scaffolding, enormous formwork, armies of skilled laborers. That's fine for a cathedral. Not so fine for a family of 4 in Idaho. Enter Wallace Neff, 1941, California architect. Already famous, already successful. But Neff was obsessed with a question nobody else was asking. What if we could build a dome, fast, cheap, and without scaffolding? His answer? Inflate it. Neff developed what he called the bubble house. You'd pour a concrete floor, attach a fabric balloon, inflate it into a dome shape, spray concrete over the outside, deflate the balloon, walk inside, simple, elegant, genius. And it failed. The concrete cracked as the balloon shifted. The thermal performance was poor. The interiors were raw and uninviting. The press mocked them. Igloo homes, blister houses. Neff tried and tried, but he couldn't crack the problem of how to keep the form stable while the concrete cured. He was a decade too early, and the world moved on. But the idea didn't die, it just waited. Enter 3 brothers, David Barry and Randy South. Not famous architects, not academics, just 3 guys from Idaho who'd become obsessed with the same dream. They'd read about Neff. They understood the physics. They believed, deeply believed, that the dome house was not just possible but inevitable. So they started experimenting, and they failed, just like Neff. The concrete cracked, the structure shifted, the proportions were wrong. But then, and this is the moment that changes everything, they flipped the process. Instead of spraying concrete on the outside of the balloon, what if they sprayed it on the inside? What if the airform stayed inflated permanently as the insulation layer of the building itself? What if the sequence was inflate, foam, rebar, shotcrete, all from the inside, with the balloon holding its shape the entire time? They tried it. 1976, Shelley, Idaho. The first true monolithic dome home. It worked, it stood, and it has stood ever since. Let me walk you through how one of these things actually gets built. Because once you see it, you can't unsee it. Step 1, the floor. You pour a standard concrete foundation, circular. Embedded in the perimeter is an inflatable tube called the tendon. That's what you're going to anchor the airform to. Step 2, the airform. This is a giant fabric membrane. Think of it like a massive balloon made from specially designed PVC fabric. It's laid flat across the foundation and attached around the edge. Then you turn on the fans. Within a few hours, you watch a flat piece of fabric rise. Slowly at first, then faster. Curling upward, billowing, finding its shape, until it's standing there. A perfect dome, 40 feet high, 60 feet across, just air and fabric. And here's the thing nobody tells you. You do all the rest of the construction inside, while the dome is inflated, while it holds its own shape. Step 3, the foam. Workers go inside with sprayers and coat the entire interior surface of the airform with polyurethane foam. Inch by inch, from the floor to the crown. This foam becomes the permanent insulation, and it bonds the rebar to the fabric. Step 4, the rebar. Steel reinforcing bars are pressed into the foam in a grid pattern across the entire surface. The dome's shape, all that beautiful geometry, is now locked in place. Step 5. The shotcrete. High-pressure concrete is sprayed in layers over the rebar. It fills every gap, bonds with the foam, creates a shell, typically 3 to 4 inches thick, that is now fully reinforced concrete. You're not building walls. You're not assembling floors and ceilings. You're creating a shell, and when it's done, what you have is a structure with no weak seams, no joints where wind can penetrate, no wood framing to rot or burn, no drywall to crumble, no attic to leak, just a seamless, continuous arc of steel-reinforced concrete from the ground up. From the outside, it looks like it came from the future. From the inside, it feels like home. Now, here's where this gets genuinely shocking. A standard American home, wood frame, fiberglass insulation, drywall, leaks energy constantly. In summer, heat pours in through the roof, through gaps in the walls, through every joint and seam. Your HVAC system is essentially fighting a losing battle 24 hours a day. The average American family spends around $2,000 a year on energy bills just to maintain a comfortable temperature. Now look at a monolithic dome. That polyurethane foam layer, the same foam you just watched get sprayed on the inside of the shell, provides an R value of around R30 to R40 continuously across the entire surface. No gaps, no thermal bridges, no cold spots. And because of the dome's geometry, air circulates naturally. Hot air rises to the crown and gets captured or vented. The interior temperature stays remarkably stable without mechanical assistance. Dome homeowners routinely report energy bills 50 to 75% lower than comparable conventional homes. 50 to 75%. Some report even more. There are documented cases of dome homes in Texas, running their AC for 3 months a year and paying less than $50 a month in electricity. A normal house leaks energy like a sieve. This one stores it like a thermos, and that's before you start talking about the lifespan of the structure. A wood frame home has a functional lifespan of maybe 50 to 100 years before major structural intervention is needed. A properly built monolithic dome, engineers estimate 500 years, minimum. The pantheon is heading toward 2,000. But let's talk about what really separates these homes from everything else, because this is the part that stops people cold. 2011. Joplin, Missouri. An EF5 tornado, the absolute maximum on the scale, tears through a residential neighborhood. Wind speeds exceeding 200 miles per hour. Buildings are not just damaged, they are erased. Concrete slabs wiped clean, cars thrown hundreds of yards, an entire neighborhood reduced to splinters, and in the middle of the destruction zone, a monolithic dome home. The windows were blown out, the door was gone. But the dome? Standing. Not cracked, not shifted, not leaning, standing. Everything around it, gone. The dome, untouched. Let's go to Louisiana. 2005, Hurricane Katrina. One of the most devastating natural disasters in American history. Wind, water, catastrophic flooding. Neighborhoods along the Gulf Coast don't just flood, they cease to exist. A cluster of monolithic dome homes near the coast takes the full force of the storm surge. When the water recedes, every conventional structure in the area is destroyed or condemned. The domes, standing intact, ready to be lived in again.